We turn now to the topic of infinite series. If you're following along in the Thomas Calculus textbook, this is section 10.2. I want to start off by, first of all, distinguishing them from sequences, which we just learned about. So an infinite series is the sum of all the terms in a sequence. That's the relationship between sequences and series. A sequence is basically when you just list all the terms one after the other. A series is when you take all those terms and add them up. So for example, we can define a sequence such as this: 1, 1/2, 1/3, 1/4. As we can see, this is really just defined by the expression 1 over n. But if instead of just listing those terms separated by commas, I take them and add them all up, as in 1 plus 1/2 plus 1/3 plus 1/4, that is referred to as an infinite series. Um, so we write an infinite series this way. And again, we leverage what we know about sequences to write the definition of a series. An is the general term of a sequence. We describe its corresponding infinite series by this expression. It's the sum from n equals 1 to infinity of an. That summation symbol that you see written like this is a sigma. That's the capital Greek letter sigma, so I should write it actually with a capital S. And of course it stands for sum. We saw that the integral sign itself looks a little bit like an S, so this is another thing that's suggestive of a sum, but it's a different kind of sum than an integral. Many of you have seen this already in an algebra class, but you probably learned about, let's say, n equals 1 up to 10, where there was a finite number on top. So instead, what we're using is on top, we're going to write an infinity, indicating that we're adding up an infinite number of terms. Now, I want to emphasize that this expression actually means two separate things. First of all, it refers to the series itself. In other words, simply the list of terms separated by plus signs. That's the concept of taking all the terms in a sequence and adding them up. That is distinct from point number 2, which is it also refers to the sum of all those terms if the sum exists. It's not always the case that the sum exists. For example, if I were to add up, let's say 1 plus 2 plus 3 plus 4 plus dot 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 forever, in other words, all the positive integers, I don't think that I'd have to do much to convince you that that would add up to an infinite number. An infinite number is not a number. So it's this, we would say the sum does not exist, the same way that infinite limits don't exist. On the other hand, if I add up 1 plus 1/2 plus 1/4 plus 1/8, etc., I don't know if you have a sense of whether that does add up to a finite number. It actually does, and we'll get to that shortly. The point is that there are some times that you add up an infinite number of terms and you get a finite number, and sometimes when you get infinity. Um, so in the case where you get infinity, we would say the sum doesn't exist. But sometimes when you add up an infinite number of terms, you do get a finite number. In that case, that's where the definition number 2 comes in, where this refers not only to the concept that we're adding up all the numbers as you can see in both of these examples in the lower left corner, but in the case of the second one, where that actually adds up to a finite number and the sum really exists, it also refers to the sum itself. Just cover a little bit more terminology here. If the sum of an from n equals 1 to infinity is a series, we refer to ak as the kth term in the series and also of the sequence. So you can see that down here. I'll just highlight this. If I have the series an is 1 over n squared for n greater than or equal to 1, then 1/9 is the third term in the sequence, but it's also the third term in its corresponding series. So whether I'm talking about listing the terms one after the other as in 1 comma 1/4 comma 1/9, or adding them together as in 1 plus 1/4 1 plus 1/9, 1/9 would still be referred to as the third term. So anyway, I hope that I've made the point that series and sequence are different. Many people get them confused. I used to have this theory that it's because sequence series, because in the English language both of them begin with the letters SE, and both of them begin with the sound C, as in sequence and series. I suppose there's a slightly different phoneme there, but that was my theory as to why people confuse them. But really, I think what it is that as we start to solve problems, because the problems look very similar but they're different, people often don't keep straight in their mind which type of problem we're solving. So I just want you to be aware of this, that as we go on, it's going to be very tempting when you see a series to say, oh, I can answer that question, but you're really thinking about a question about the sequence. So you really want to keep straight in your mind whether we're talking about a series or not. And it's really not that hard. When we're listing the terms, it's a sequence. When we're adding them up, it's a series. But they have different questions that can be asked about them, and even when there are similar questions, they're often going to have different answers.